However, macromolecules is a pretty complicated topic that we're going to just scrape the surface on. And I find that it is beneficial to spend some time talking about these molecules and what these words mean, because you're going to see these words for the rest of the year. So if you do not understand macromolecules now, you're going to be confused for the next multiple modules. As we will keep building on these, and we will even go into a lot more detail on some of these molecules. Right, so keep in mind this is scratching the surface. This is also starting to get at biochem. So if this is something that interests you, biochem may be in your future. That's fine, Lane, as long as you're listening to me talk about macromolecules. All right, I got all this stuff open. Zoom wants me to update. I'll never update Zoom. Never. Okay. So let's start with a little warm-up question, which is, what molecules or molecule do you know about in the body that you think is important? So listing a molecule that you already know. If you've already been through the lesson, you probably know a lot more molecules than you did. But what molecules do you know about that you've already heard about, that you learned about in middle school, that you think are important? The ones in your gut that help you digest food. Thank you, Lane. That is an excellent example. Those are called enzymes. We will be talking about those in extreme detail. DNA, very important one. RNA, also very important. However, do we even know what RNA does? You will at the end of this class. Not today, but the end of the semester, right? Acid in your stomach is different from the enzymes, but still important, yes. So DNA, RNA, enzymes, acids in your stomach, which wouldn't really necessarily be a macromolecule, but yes. So there's many, right? Nobody said anything like structural proteins, right? Like things that make up your skin and hair could be considered important, I would think. They give you your shape, right? Bonnie says water, incredibly important. However, not a macromolecule, which we'll discuss why maybe that is. Amino acids, yes, although amino acids are not the acid in your stomach, Lane, so they're different things. But great, so we know some stuff, right? We know some molecules, right? The assumption here is that you probably have heard of some molecule in your body at this point in your life, I would hope, right? Or else you've been really good at ignoring everybody telling you about molecules in your body. So now we're going to talk about the four major ones that really are the most important for living organisms, right? Of course, there are way more other types of molecules. We're not going to talk about them in this class. We care about the macromolecules. We're going to talk about the building blocks, the elements, and the structure of these molecules. Like I said, this is going to become biochem right now. So what is a macromolecule? Well, does anybody know what the prefix macro might mean, or have a suggestion for what it does mean if you know? It means big, right? Seems obvious, but we're talking about big molecules. In biology, we don't usually go too much smaller than these macromolecules, right? For example, we don't really talk about atoms or properties of atoms or things that atoms do. Of course, all that stuff is still happening. We just don't really talk about it in biology. However, if you major in biology, you're in for a lot of science, because you have to take a year of physics and 2 years of chemistry at the very minimum, right? So you will learn about all that stuff in excruciating detail. Lane brings up an excellent point, which is that macro is the opposite of micro. Exactly. So if you're having a hard time visualizing, think about micro. So now, if you did this lesson already, because I know a few of you turned in your paragraphs, then silently in your mind think about this. But everybody else who hasn't seen this yet, or maybe did see it but you already forgot, because that's possible, see if you can order these four words from smallest to biggest. Which one of those things is the smallest and which one is the biggest? And feel free to type your answers in the chat. Okay, Lane is on it today. Atoms are the smallest, which it seems like Joelle is agreeing with that. Then molecules, then macromolecules. Then I like how Colin puts a question mark after cell, and Bonnie did as well, right? Because that might have been the point where you thought, okay, big molecules and cells. What is the relationship there? Right, well, all of these macromolecules that we're going to learn about are found inside your cells. So yes, cell is the biggest. Now, some of these macromolecules can also be found outside of cells, and in some cases might feel bigger, right? But they're not really. They're actually small enough to go in cells. Then Lane's getting us to something we'll talk about in second semester, cell, tissue, organ system, right? Exactly, more organization. A lot of biology is about organizing. How does the body organize? What does the body do to organize? And I bet a lot of you guys are really happy that we're not talking about math right now. So the answer was atom, molecule, macromolecule, then cell, right? So think about it this way. DNA is a macromolecule. It fits inside your cell. Let's see. Joelle asks, is biology like anatomy? Because it's like the makeup of the body. Sort of. We don't really talk about bones and muscles necessarily. We very briefly will touch on the systems of the body. Mostly, at least in this first semester, we're going to be talking about like microscopic things that you can't see. We're going to be talking about cells. We're going to be talking about processes that happen inside cells. And a tiny bit, we're going to be talking about genetics, which does have some, well, we're going to be talking about genetics a lot, but part of genetics will be like bigger stuff. But for the most part, it's a molecular focus. Will you relearn this in med school? No, they'll assume you already know this in med school. Yeah. And in college, you will learn even more detail about these molecules. Like you'll learn about their bonding and the different chemical properties that they have, and so much detail that you will either really love it or you will regret your decision to be in med school. Okay, so remember, we already kind of talked about this. Macro just means big. We're dealing with large molecules that are necessary for the function of life. However, they are smaller than cells. So just because they're big does not mean that they're, the size of you necessarily. So we have four groups of macromolecules. They are the carbohydrates, lipids, proteins, and nucleic acids. The complication here is that a lot of these words, proteins and carbohydrates specifically, we hear about in our everyday regular life. Who could create a sentence that's not necessarily a biology sentence with the word carbohydrate or protein in it? To give us an example, like let's say your mom is talking about one of these things. Like what's something that a mom would say? Perfect example, Joelle. Is butter a carbohydrate? Yep. Right? You should eat carbs for strong bones. Cut my carbs. Soda has a lot of carbs, right? We hear about these things all the time. Mean Girls reference? Yes, right? Is butter a carbohydrate? That's what I should have said. I should have said, what would a mean girl from Mean Girls say? Yeah, right? Is butter a carb? You're so skinny, eat some protein, right? Yeah, we hear these things all the time. We are not talking about nutrition, carbohydrates, and proteins necessarily, right? Of course, the molecule itself, carbohydrate, right, is the same as the nutrition carbohydrate that people are talking about, but that is not the same way that we're going to be using these things, right? So we don't think of cells as like needing protein to become strong or whatever, right? You might think of it that way if that helps you, but that's not really like the science way. Is mayo in instrument? What? I don't know what that means. But I'm guessing that's a SpongeBob reference since Joelle came in with a Patrick comment. Yep, okay. So we have four of these. I have created a chart for you of these molecules, and it's going to be your best friend. So here is the chart, which I thought I had posted into Canvas, but this morning I didn't see where I'd posted it, so I posted it again, just in case you did not see it yet. This is a really helpful chart because it tells you examples, it tells you the building blocks, it tells you the elements, and it shows you the actual chemical structure, right? So I would save this to your Google Drive. If you don't know how to do that, you come up here to where you see the Google Drive symbol with an arrow, right? And you click adding to my drive, and it adds it to your Google Drive. So that's helpful if you need to reference this. Now, we will have a small test in this module, probably not as hard as the statistics test was. It will be a lot of vocab and critical thinking. But mostly for the rest of this course, we're going to have projects, or I hate to say the word essay because it's not going to be like an English essay, but we're going to have a lot of writing and projects to demonstrate your learning, right? So it's important to know the vocab so that when you're using it correctly, which is why if you've already started the assignment for this, right, I had you write a paragraph using these words. It's important to be able to use science words correctly. And when you know what they actually mean, you'll start to see some people out in the world, right, using them incorrectly, and you'll go, what is this person doing? They clearly don't know about science. Yeah, so it's due today, Joelle, so you're not technically behind, but some of you guys are overachievers and already turned it in. So looking at this chart, that's what we're going to go through right now. What are all of these molecules, and what do they mean, and what do they do, and why do we care about them? Or at least, why does biology care about them? So for each one of these, we're going to talk about the elements from the periodic table that create this structure. Carbohydrates always have carbon, hydrogen, oxygen. That's all they have. If there's a nitrogen in there, it's not a carbohydrate. If there's something else in there, it's not a carbohydrate. CHO, show, that's it. Right? In fact, they also have this interesting math connection, ooh yay, where they're always in a ratio of 1 to 2 to 1. You always have twice as many hydrogens as you have carbons and oxygens. Now, that still gives you a ton to work with here, right? If you have these three elements, they can be arranged in a variety of ways, and they can be shown in a variety of ways. In this case, we're looking at two pictures of glucose and fructose, which are two simple sugars. And these simple sugars are shown here in an elongated structure. They can also be in rings, which I'll show you on the macromolecules chart in a second. So a lot of that is like some intense chemistry stuff. But regardless, if you look at a molecule and you see CHs and Os, one of your first thoughts should be, this could be a carbohydrate. Now, lipids. Lipids are also CHO. Right? So it won't help you necessarily know it's only a carbohydrate. It could also be a lipid. However, the structures look very different. So let's take a second right now. Looking at these two pictures of lipids, which by the way, lipids is a fancy word for fats. Right? You never hear nutrition people saying, oh, can I get my lipids in for today? Right? Although they definitely could be saying that because they are fats. Bonnie is pointing out they don't have the same ratio. That's definitely true. Lipids don't have a 1 to 2 to 1 ratio. They can, I think it might be possible, but that's not a common thing for them. What else do you notice? I'm going to flip back to the carbohydrate one, maybe. Look at the carbohydrate structures. Absorb them, take them in. And then look at the lipid structures. Right, they look pretty similar. You see there's like a carbon backbone. However, I see a lot of OHs on carbohydrates, whereas lipids, I just see straight up H's. Right, so you're pointing out a great thing, Lane, which is that there is a difference between the types of fat, right? Saturated versus unsaturated fat. That's, again, more of a nutrition thing. We're not necessarily going to talk about that, right? But because of this double bond, some lipids are curved. Now, in baby science classes, which is unfortunately a lot of classes, you'll see structures of carbohydrates written out like this. In real chemistry, we actually write carbohydrates as rings. So you will also see them like this, where they are a ring structure. Right? So carbohydrates are rings, lipids are not. Lipids do not make a ring. It's just not something that they do. It becomes even more apparent when you see the carbohydrate as a ring and you see lipids with all these H's, right? That clearly they look pretty different structurally. All right, I'm kind of jumping around. Sorry, I get really excited about biochem. In fact, I'm kind of wishing that I would have majored in it when I took biology as my major, but I wasn't that interested in molecular stuff at the time. So, moving on. Lipids are made of something called fatty acids. We'll talk about that in a second when we look at the chart. Proteins. Proteins are really complicated now. You might look at that picture and think, haha, that looks funny, right? Or that looks ridiculous. That's actually a real representation of what a protein looks like, right? In fact, there are people who spend their life creating the structure of a protein as a digital representation on the computer. Art and science combining. Proteins contain way more complicated stuff. We've got carbon, hydrogen, oxygen. We also have nitrogen, phosphorus, and sometimes sulfur. Now, that doesn't necessarily explain all the squiggly squiggles you see here, right? In fact, you probably noticed there's like little curly things, there's longer strands. This one doesn't even have beta sheets in it that I can see, but there's another kind of folding. So really, this is representing the way that the protein folds. So proteins have very, very specific structures. Think like a key and a lock. If you take your key and you try to go into your neighbor's house, right, it probably won't work. I mean, if it works, that's insane, but it shouldn't work, right? And you'll probably also have people saying, why are you trying to get my house? Which is a separate thing. But proteins have a very specific structure that tells them what their function is. If their structure is changed in any way, they usually can't work. There are some genetic diseases that involve that concept where your protein is messed up, right? Like lactose intolerance. If you have a hard time digesting lactose, right, which is a protein, imagine, found in milk, your lactose digesting molecules, your enzymes, don't work. So when lactose enters your body, it chills in your stomach and can't be digested, and then that's why it makes you feel sick, right? So proteins can actually break down other proteins. That's one of the things they can do, and they can also cause problems. Regardless, they're made of amino acids. Again, we'll talk about that again, but they are chomps, is a way to remember. Nucleic acids, right? One of the more commonly talked about molecules now, thanks to, DNA becoming a thing that people talk about in regular life, right? Kendrick Lamar even has a song about it. Most people know what DNA is. That was not the case when I was your age, right? If you talked about DNA, people were like, huh? But now pretty much everyone knows what that is. So that one might resonate with you because you're like, yeah, DNA, that's something I know, I've talked about, blah, blah, blah. Nucleic acids are made of CHOMP, carbon, hydrogen, oxygen, nitrogen, phosphorus, right? If we look at the structure of DNA, we see a sugar phosphate backbone. The sugar is a ring, right? Remember I said sugars come in rings, and the phosphate is located right here where the P is. And then we have these nucleotide, well, actually this whole thing is a nucleotide. We have these nitrogenous bases, which we will talk about, which are part of DNA. They also have a ring structure. Rings are pretty common in organic molecules, which are molecules found in living things. Also, a lot of ringed structures cause cancer, as a fun fact, but hopefully we don't find those in living things. So, macromolecules chart, I said you have to know this. We're going to talk through it really quickly. And again, I know this is like maybe not the most exciting because it's me telling you stuff, but this is pretty hard information to digest by yourself, right? Please ask questions in the chat if you're like, what are you talking about? Or repeat or whatever. So we're going to start with the carbohydrates again. They are usually ringed structures. You might see them not as rings. I will always show them to you as a ring minus that PowerPoint that I just did. In fact, I'll probably replace that with a ring. They're made of CHO as their elements, right? Again, they're usually in a 1:2:1 ratio. Building blocks, meaning what are the small molecules that create this macromolecule? Because remember, this is a big molecule. So it's almost like taking two Legos and putting them together to make a bigger Lego. So in this case, glucose can be a building block. Sugars are another way that you hear a building block, or you hear this fancy word called monosaccharide. What does this word mean? Or what do we think it might mean? What does mono mean as a prefix? It means one. I saw 2-1 and I was like, what, Lane? Yeah, it means one. So this means one sugar, right? A saccharide is a sugar. So if monosaccharides are one sugar, then what do you think a polysaccharide is? 2, it means really many. So monosaccharides are a single sugar. Polysaccharides are bigger sugars. Starch is actually technically a carbohydrate, right? Something that we're all familiar with. Starch, most common starch probably people think of as like a potato or corn, something like that, right? Starch is a big carbohydrate. In other words, it's not a simple sugar. It's more complicated than that. We also have polysaccharides, which are big sugars. Those would be like maltose, dextrose. There are also disaccharides. There's a lot more detail here. This is the bare bones, like I said. Other examples of carbohydrates that are less known. Cellulose, also known as a cell wall. Right? We can't digest cellulose, but we can digest carbohydrates. Why? How would that work? How come we can't digest cellulose if we can digest carbohydrates? That's a carbohydrate. Yes, it is. How is that possible? That you could eat sugar and you're fine. You eat a cell wall and you can't digest it. In fact, it's known as fiber, right, in the nutrition world. It has to do with the bonding, right? So the way that the glucose molecules are bonded in cellulose, we actually cannot break it down. It is thought that the appendix potentially maybe used to break cellulose down. And because we don't really need to break cellulose down anymore because we have so many food sources, right? We're not just like in the woods eating random plants off the ground hoping that we're not going to die, right? The appendix really, we don't use it anymore. In fact, it causes a lot of people a lot of issues. You can have it removed. You can be fine without it. It's thought that in hundreds of years, potentially thousands of years, the appendix will be gone because we won't need it. It's not used. We'll talk more about that when we talk about evolution, but it is thought that the appendix originally did help digest cellulose. Also, the exoskeleton of insects. You know, when you step on an insect and it makes a crunch sound, and maybe you feel sad inside, or maybe you feel happy because you killed it, that's made out of chitin, right? Chitin is pretty strong. If I told you that it was made out of sugar, right, you would probably go, wait, an insect's skeleton is made out of sugar? That seems insane, right? Well, it is. It's sugar. Again, it's the way that it's bound together, right? So again, we cannot digest chitin, right? I mean, some people do eat insects. Chitin's also found on shellfish, right, in a thicker form. So you think about your shrimps, your lobsters, right? They also have chitin exoskeletons. So all of that stuff is made out of sugar. Hopefully a few of those were new things for you to hear about. Lipids. When we see the structure of a lipid, we actually see a backbone with these 3 things called fatty acids. Isn't chitin made out of elephant tusks? No. Because then we would need elephant tusks for insects to exist, and that doesn't really work. So if you see these 3 chains of fatty acids all connected together, it is a lipid, also made out of CHOs. Thankfully for lipids, they're a little bit more simplistic. They only have one building block, and that's fatty acids. There's no other ones. Examples of lipids would be steroids, right? And I'm not talking about like steroids like you're trying to get, big at the gym or whatever, swole as it is called, right? No, we're talking about naturally occurring steroids in your body. Cholesterol, right? Testosterone, which we all have, even people who are female have testosterone, right? It's a steroid. Also lipids. So oils found inside of your body and other fats inside your body are considered to be lipids. You like that? Lipids are an example of lipids. And waxes. So earwax is made out of lipids. Pretty exciting. We really won't talk too much about lipids in this class, but they are really important for biology, surprisingly. I don't know, I was surprised by that at least. Nucleic acids, right? We talked about the CHOMP as the elements that make up a nucleic acid: carbon, hydrogen, oxygen, nitrogen, phosphorus. If you don't know what those words mean, by the way, you should be writing them down. Type a 1 in the chat if you need me to spell those things out for you in the chat. Okay. Carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur is the S, if you see sulfur. Right, so make sure you know what those letters mean, because if I ask you a question about CHOMP and you're like, what the F is that, then that's not good. You should be like, oh yeah, carbon, hydrogen, oxygen, nitrogen, phosphorus, and sometimes sulfur for proteins. Okay, building blocks of nucleic acids are nucleotides. We will define in great detail what a nucleotide is. So have no fear, just for now, know it's a building block for DNA and RNA, which are two main examples of nucleic acids. Aren't those all gases? That is a great question. If we're talking about existing at room temperature on Earth, yes, except for carbon. But when they're bonded together, they are not, right? Nucleic acids would be solid at room temperature. They're just really, really, really small. Okay, proteins, the final one that we will talk about a lot this year, as well as nucleic acids. Proteins are CHOMPs, right? Carbon, hydrogen, oxygen, nitrogen, phosphorus, and S is in parentheses because it's sometimes. Not all proteins have sulfur, but some do. The building blocks for proteins are something called an amino acid. Again, we will talk about in great detail what that is. Examples of proteins include enzymes, which are going to be the one that we really focus on. Those are molecules that build and break stuff down. So not next week, but the week after, we will be doing a liver enzyme lab. By we, I mean I will be doing it and you will be watching and helping, where we're going to talk about enzymes working. And I will offer actually that you can come on campus if you want to see it in person, because I will be on campus for that. But you don't have to. You can totally watch it online, and it'll be the same experience, but you won't have to smell or touch the liver. There's also receptor proteins, which we'll talk about. They're on cells. They have a very important function. Signaling molecules are proteins. Transport proteins, right? Basically anything in your body that you're like, I'm not sure what it is. It's probably a protein. So if you ever have to guess protein. Proteins make up almost all of the the structural components of your body. Okay, which is why in nutrition, right, they say protein's so important. All right, so macromolecules chart we just discussed. Everyone added it to their drive, I hope. Now we're going to do a practice question. This is a pretty challenging question. So I'm going to read it to you, and then you're going to guess 1, 2, 3, or 4 as your answer here, or hopefully you know. The soil of a rose plant is lacking nitrogen. Which one of the following would the plant have the most difficulty synthesizing? Colin says 2, Joelle says 3, Bonnie says 1. Ooh. Thank you, Lane. 4 is the correct answer. So let's talk about why. Let's talk about how I knew. And hopefully how Lane knew, unless Lane was just guessing a random one, which is also fair. Okay, so if nitrogen is lacking, right, I want to think which of my molecules, you used your notes, excellent. Which of those molecules actually have nitrogen in it? So I'm going to start with starch. Starch is a what? Is it a carbohydrate? Is it a lipid? Is it a nucleic acid? Is it a protein? Which one of those is it? It's a carb, right? A carbohydrate. Do carbohydrates have nitrogen? Nope. Goodbye, starch. Wax for the leaf. Wax is which one of those macromolecules? Is it a carbohydrate, lipid, nucleic acid, or protein? It's a lipid, right? Actually, I had this kid one year who every time we said lipid, he would do like a loser sign on his head, and he was obsessed with it, and he got every question about lipids right. And now every time I say lipid, I think of that. Anyways, wax relief. So do lipids have nitrogen? Nope. What about glucose? Is glucose a carb, lipid, protein, or nucleic acid? Glucose is a protein? Carb, a carbohydrate, right? It's a simple sugar. Do carbohydrates have nitrogen? We already established no, they don't. So we're left with DNA, which we would hope is the right answer, but just in case, we will confirm, right? DNA is which type of molecule? It's a nuke acid. I like that abbreviation. Yeah, it's a nucleic acid, which if you look at your macromolecules chart, which you are welcome to look at for this, has carbon, hydrogen, oxygen, nitrogen, phosphorus, and no sulfur. So it's CHOMP. So DNA would be the correct answer here. So these are the kind of questions that could apply to the real world here, right? For example, nitrogen fertilizer helps plants grow, and one of the main reasons that it does, right, is that it actually can help speed up their ability to divide their cells quicker and create DNA and grow in size, right? So all of these things matter in terms of like real things that you see in a plant or an organism. Now, nitrogen can also hurt some plants if you have too much of it, but we're not going to talk about plants because whatever. Okay, a monkey's body is low in protein. Poor monkey. He is lethargic. What does lethargic mean? It's like a bonus English question here. Well, okay, you're already guessing the answer. I'm asking what lethargic means. What does lethargic mean? Some of you guys seem like you're a little lethargic today. Tired, yes, right? He's tired and he's unable to lift heavy things. No energy, right? Could be because of low protein, could also be because of 1,000 other things. Which element is most likely missing from his diet? Again, this is like a gross oversimplification, but it's to help you get the molecules and what they're made of connecting. So he's low in protein. What is he most likely missing out of these 4 things? I like how a lot of people are saying 3, nitrogen. Oxygen is being thrown out there as a possibility. Thank you, Lane, for giving us a lovely definition of lethargic. So let's break it down. Let's think about proteins, right? I'm going to show you guys like how I do this myself. I would go to my macromolecules chart, which disturbingly I have memorized, obviously, because I've been teaching biology for a lot of years. And I'm going to confirm, all right, proteins, let me look at that one. They have CHOMPs. So carbon, hydrogen, oxygen, nitrogen, protein, phosphorus, and sulfur. Okay, so I'm going to go back to my list. Well, I see carbon, oxygen, nitrogen, and sulfur. So that's a problem. Now I have to think, though, what is special for protein? Is carbon in some of our other macromolecules? Yeah, right. It's in all of them. It's the basis for life. Is oxygen in our other macromolecules? Maybe I don't remember. Okay, but yeah, it's in nucleic acids, it's in lipids, it's in carbohydrates. Okay, what about nitrogen? Nitrogen is only in nucleic acids, and sulfur is only in some proteins. So that's like a tricky one then. Which one should we pick, nitrogen or sulfur, if we're really just focusing only on proteins here? Yeah, I think 3 is the best answer. I would also accept 4, right? This is kind of a discussion-y question, not necessarily a question I would put on a test. But keeping in mind that in this type of critical thinking, I want you to figure out what is special about a protein that other stuff doesn't have. Carbons and everything. oxygen's in everything. Nitrogen is only in protein and nucleic acids. Sulfur is only in some proteins, right? So really thinking about which molecules make up and how they would be synthesized. For example, if you don't have nitrogen, you wouldn't be able to make a protein. You could make a carbohydrate though. Okay. Final little practice thing, analogies. So I'm gonna give you guys, don't put anything in the chat yet. Take a second to let people read. Amino acids are to proteins as blank are to nucleic acids. And the second one is monosaccharides are to polysaccharides as fatty acids are to blank. So take a second, look at your macromolecule chart. See if you can figure out what you think should go into those blanks. And if analogies are really hard for you, don't worry, I'm gonna break it down. But it's a different kind of challenge to think about the relationship between these words. That's okay, Elaine. All right, type a 1 in the chat if you think you kind of have an idea and you want to go over it. Type a 2 in the chat if you're like, I'm still thinking about this. We've got 11 people and I see 2 1s and no 2s. Okay, thank you, thank you, thank you, thank you. Kobe, do you have a sleepy emoji as part of your name? How perfectly representative of you that is. Okay, so, but I'm glad you typed a 1 in the chat. Let's talk about the first one. Amino acids are to proteins as blank are to nucleic acids. Well, Lane kind of already gave us a possible answer here, nucleotides. Do we agree with that? Do we think it might be something else? Bonnie says yes, as in agree. I also agree. So what were we looking at here? Well, we were looking at the relationship of building block to molecule. So amino acids are the building blocks of a protein. So then we go to the chart and we say, okay, well, what's the building block for a nucleic acid? Well, it's a nucleotide. Now, again, I'm using these words pretty easily because I already know what they mean and I know all the stuff you're going to learn about them in the future. If you feel confused about the actual word, it's okay. Right now, I just want you to understand the relationship between these words. That amino acids build proteins. Do you have to know what an amino acid is? Do you have to know how that happens? Not yet. Okay, what about for the second one? This one's a little trickier. Monosaccharides are to polysaccharides as fatty acids are to what? Any ideas for this one? Carbohydrates as a guess, amino acids as a guess. Hey, I'm happy you guys are throwing vocab out. Proteins. Okay, well, let's break it down. Monosaccharide is the building block of a sugar, right? It's a simple sugar, it's a tiny sugar. So we're saying small sugars are to big sugars. So guess what? It's the same relationship. It's a building block to a bigger thing. So fatty acids, you could write many things here as long as they were lipids. So Bonnie's answer is perfect here. Oils, you could write fats, you could write lipids, you could write waxes, you could write any type of lipid you could list there. Because fatty acids are the building blocks for a lipid. Right? So lipids is probably the most like logically one, but oils, fats, and waxes are also appropriate answers here. Okay, so you will definitely have one analogy that'll probably be really similar to these analogies on your test at the end of this module. So if you were here, you're going to get extra knowledge of how to answer these, right? But most likely it'll be building block to bigger thing, because that's a pretty easy one to do. And it's easy for people to see the relationship there. Okay, so now what you're doing for this assignment is you're using the following words or phrases in a paragraph correctly. I saw a few people who turned this in who were just like listing the words out and kind of just like throwing them all in a thing. This is for you to make sure you understand what the words mean, because later on I'm just going to start talking about the words, and if you don't know what they mean, it's going to be confusing to you. Chomp was the one that most people did not talk about. Guess what? Because you needed this virtual session most likely to understand what that meant. So if you did already submit this and you didn't talk about chomp, I was kind of nice to you, but I recommend you go back and look at it, right? And make sure you know what chomp is. The other part is just answering questions about macromolecules. One of the biggest themes of this class is that structure determines function. Structure determines function, right? I would say it with me. You don't have to unmute yourself, but structure determines function. So we're going to start with the structures, right? What do these molecules look like? What structure do they have? What elements do they have? That's going to tell us what they can do and what they are capable of doing. Okay, sorry, I get really passionate and rant about biology, as you guys will see. So that's going to be the assignment that you're doing today. Because you attended this virtual session, you will be getting a code word that I'm about to type into the chat right now. It's a pretty duh one if you were in the virtual session, but regardless, that is the code word. That code word can be used for 5 bonus points on any assignment. So go back in module 1. It is a dull word. It doesn't have to be capital. So go back to module 1. Look at which assignment you aren't happy with. Figure out what you want to add your points to. You can always email me. Say, hey, I want to add my points to this. I want to add my points to this. Just tell me that you know what the code word is, right? And then I'll happily go add those points for you. You're also welcome to save it, right? If you want to save it and use it later, you can. However, right, I am telling you there's not going to be a lot of tests going forward. There will be a few, right? Because obviously I have to make sure that you're reading all my PowerPoints. But a lot of this stuff's going to be projects, which for the most part, you will probably get a grade that you want on that pretty easily, right? Last thing I'm going to say is there is an opportunity to get even more extra credit. Again, think about this. You could do it later. I don't care. You could do it the day before the semester ends because you're like, whoa, I want some 20 points on this. Are all points ranked the same? Do you mean like, are they worth the same? So if you add it to, oh, I see, are all, no. So tests and projects are usually weighted more, right? So basically I don't have categories. I do it by number of points. So if an assignment is over 50 points, that means it's important and will impact your grade more. If it's less than 50 points, then it's like a daily work assignment. That's how I have it set up right now, is that it's weighted based on the number of points. So that quiz for module 1 was 23 points. So really it's not impacting your grade very much, right? But if it's the thing you got the lowest score on, then you can add your points to that for sure. And if you want, I can also add it to 2 things and tell you which one gives you the most points. I'm happy to do that. So here's an opportunity for extra credit. This will live forever on the PowerPoint, so you can always go back if you want to do the extra credit in the future, you want to do it now, however you're feeling. I did want to say one last final thing before we go, which is make sure that you're reading the lessons, right? I'm seeing some people turning in work that I can tell from your first sentence you did not look at the lesson at all. Right? The purpose of the lessons is that I've broken down the material and I'm giving you access to the material that I want you to work on in that exact moment. There will be some things that are way open-ended where it is go find something, do your own thing, right? Not all the stuff is like that though. So for example, the theories of life discussion prompt is related to the 7 theories of the origin of life lesson that I created for you. This is not theories that you're inventing or that you've heard or that you think. No. I don't care what you think. I mean, I do, but not for this discussion. I care, can you look at these theories and give me a critical analysis of them, right? Can you tell me which theory has good evidence that you're like, okay, that seems like it could have happened, right? Again, I don't care if you believe the theory. You could think all of them are insane. That's fine, right? It's not about your belief or your feelings or your opinion. This is straight up science facts right here, right? And part of that is actually being able to look at someone's experiment and determine whether that seems plausible. So make sure that you're actually looking at the lessons. They're all labeled lesson 2, then there's something, lesson 3, then there's something, lesson 4. Right? All of them are lessons that I created. It's not like read 50 pages, right? It's all chunked already for you. So please look through them so that I don't have to keep redirecting you back to them. Yeah, I know it sounds kind of savage, Kobe, but it's true, right? It's a waste of my time and your time if you're just doing some work that doesn't make sense and isn't related to the class. So keep that in mind. Also, I'm about to publish a bunch more stuff in the class. Obviously, the class does not end on October 16th. That's just all that you feel targeted. No, actually, Lane, I probably wasn't even thinking about you when I decided to rant about this. It wasn't just you. I had a lot of people do this. That's why I'm bringing it up, right? It was like, I saw about 6 people that I was like, yep, they didn't read the lesson. So it will save you time if you read the lesson, because then the assignment is much easier. So make sure that you are doing that, right? And also another thing about virtual sessions, which I know I've said in other classes, right? The virtual sessions are designed to be on the hardest content, or they're designed to be collaborative, right? These are not things that you can do in advance. So today, I didn't explain chomps, chon, cho, whatever, in the PowerPoint on purpose, because I wanted you to have to come to the session to know what I was talking about. Maybe you figured it out, right? But the sessions are there for a reason, right? So you can work ahead, but don't do virtual session stuff early. It doesn't make sense. Okay, I'm done ranting about the class. Does anyone have any questions? Or are they concerned about something? Okay, I feel like I made the session end on a really intense note. But it's an intense class. You have a pun that you would like to share. Well, we'd love to hear it. But yeah, it's gonna be a really good class. You're gonna learn a lot of stuff that you didn't know, hopefully. What's nitrogen in the sunlight? That's a good question. Datrogen. Love it. Love it. Please bring all of your science jokes and puns. In fact, I might have to go back to what I used to do when I taught middle school, 8th grade science. We had a meme wall, and if you brought in a science meme, you got bonus points. So maybe I'll do that if you can find some good science memes or create them. Because you guys know I love memes. They make everything better. I had a really good ovary one that I'll have to share when we do body systems. Okay. So otherwise, that is the end of today. Make sure you're going through the lessons, right? Make sure that you're staying on pace. That you had help, yeah. And if you get stuck, right, email me. If you're concerned about something, email me. Otherwise, I will see you guys next week, where we will be debunking a viral claim from the internet and breaking down the science. Okay. Bye. Oh, thanks, Bonnie. I'm glad you liked it. All right. So tune in next week to debunk something. Bye.